Welcome to the lesson for the DN9 assignment, Centripetal Acceleration. Let me tell you about one of my most recent trips to space. Well, there I was, just swinging a rock around on a string, chilling in space with my spacesuit on. I thought to myself, what would happen if I cut the string? So I cut the string and the rock continued on its path. Same speed, same direction, forever traveling further from me on its unwavering course. I thought, man, I love that rock. I set it free, but it's never coming back. Before we start, there are a few things we want to talk about that will help us better understand what is going on in this lesson. If I throw a ball up, the force of gravity is continuously, through its entire trip, accelerating the ball downward. When the ball is going up, this downward acceleration slows the ball to a complete stop. Then it increases its velocity until it returns to my hand. If the net force was to the right, and I throw the ball to the left, the ball would also be slow to a stop and then gain speed in the direction of the net force. Imagine a rock on a string being swung over someone's head, or better yet, similar situation, but something you may better relate to. You as a kid on a merry-go-round, and as you spin around, you constantly feel like you are being pulled off. But this is actually an imaginary force caused by inertia, the centrifugal force. Your body wants to continue on its current trajectory, but some force keeps pulling you towards the center. This is called the centripetal force. You feel like you are constantly being pushed away from the center. And the reason you feel this is because you are actually constantly being accelerated towards the center of the circle. I know you are probably saying, how can I be experiencing a force pulling me inward when I clearly know I am being pushed away from the center? Think of when you are standing in bare feet. Gravity is pushing down on me, and I can feel the ground pushing up on my feet, especially when my old feet get tired and sore, and I can really feel the ground pushing me up. Or think of when you are sitting in a car. When the car is accelerating, the engine propels you forward, while you feel pulled back into the seat of the car. What you are experiencing is due to your inertia. Inertia is the resistance of any physical object to any change in its velocity. This includes changes to the object's speed or direction of motion. An aspect of this property is the tendency of objects to keep moving in a straight line at a constant speed when no forces act upon them. Imagine a ball that is being pushed by a force that can change its direction. The force is constantly trying to push the ball towards the center. When the ball is not in the center, the force pushes it towards the center, and the further it gets from the center, the harder the force pushes it towards the center. And imagine a similar force that is acting in the y-axis. Now, what would happen if both these forces were acting on the same object at the same time? Well, that would cause the object to then move in a circular path. At the top of the loop, it's a centrifugal force pulling the bottle up while gravity is pulling the bottle down. The force experienced is then the difference between the two forces. And if equal, the bottle is for a brief moment experiencing complete weightlessness. The bottle would experience a 0g force. At the bottom of the loop, the centrifugal force and force of gravity are in the same direction. If they have the same magnitude, at this brief moment, the weight of the bottle would be doubled. It would be experiencing a 2g force. just in case you thought it was empty and I was cheating you. So when it is being spun around, it's a centrifugal force that is pushing the bottle against the board surface. The force of gravity is pushing down, but it does not go down because a static force of friction is holding it in place. Here is the URL for an interactive demo. The conclusions will be on the following slide, as well as a couple URLs for sites that have some pretty interesting information about centripetal force. As the speed of an object increases, acceleration experienced by the object increases and force acting on the object increases. As the radius the object is following increases, acceleration experienced by the object decreases, and force acting on the object then decreases. As the mass of the object increases, acceleration experienced by the object is unaffected, and force acting on the object increases. Now for the formulas used in this assignment. Fc is the centripetal force, and it is equal to mass times centripetal acceleration. Centripetal acceleration equals velocity squared divided by the radius of the circle. Velocity equals distance divided by time. In this case, the distance is the circumference of a circle, and that is divided by the time it takes to do a single rotation, which is called our period. What centripetal force, so I'm looking for Fc, acts on a 28 kilogram kid, that would be the kid's mass, if he is 0.62 meters away from the center of rotation. So the middle is 0.62 meters away from the kid, so that would be the radius. In the Mad Hatter teacup ride at Disney, and the ride makes 7 rotations, so that means that's how many cycles are completed, and it's 7 cycles in 31 seconds, so that's the total time to do 7 cycles. So I'm going to use centripetal force equals mass times centripetal acceleration. I don't know AC, so I have to solve for AC first, and that equals velocity divided by radius. And I don't know velocity, so before I can use this formula, I will have to solve for velocity, and that equals 2 pi r over period. But I don't know the period, so before I can use this formula, I got to solve for the period, and period equals time over cycles. Thank you, physical science, grade 11. Look at that, coming back to haunt us. So, period equals time over cycles. I know time, I know cycles, I can sub those in, run it through my calculator. It takes 4.429 seconds to do a full rotation. Now I can go back to my velocity formula, 2 pi r over period. So 2 multiplied by pi multiplied by the radius of 0.62 divided by the period of 4.429 seconds. The velocity of the kid is 0.8796 meters per second. All right, centripetal acceleration. Velocity squared divided by the radius. Centripetal acceleration is 1.248 meters per second squared. Now I can sub that in to solve for the centripetal force. So mass multiplied by the acceleration, and that gives us 34.94 newtons. Corrected to 2 significant figures, the answer is 35 newtons. Gargamel finally catches a Smurf. He then attaches the Smurf to a rope and swings it over his head. If the rope is 1.2 meters long and the Smurf makes 82 rotations in 1.0 minutes, what is the Smurf's mass if the tension is 170 newtons in the rope? So the rope is 1.2 meters long. If he's swinging that around, that will be the radius of the circle he's making. 82 rotations means the Smurf is cycled 82 times, and the total time to do 82 rotations is 1.0 minutes, which should be in seconds. So 60 decimal seconds to maintain 2 significant figures. What is the Smurf's mass? If the tension is 170 newtons. Well, if he's swinging that Smurf around, Fc is what is causing the tension in the rope. So if the tension is 170, Fc equals 170 newtons. The situation would be different if he was looping the Smurf around vertically. Luckily, he's holding it over his head and twirling that Smurf in circles. So we'll start with force equals mass times acceleration. I want to find mass, so I need to get mass by itself. So I'll divide both sides by acceleration so they can factor out. And mass equals force divided by acceleration, but we don't know acceleration. So we're going to have to solve for acceleration using velocity divided by radius. But we don't know velocity, so we're going to have to solve for velocity. And that equals 2 pi r divided by period. And we don't know period, so we got to solve for that. So period is time divided by cycles. We do know both of those. So 60 divided by 82 gives me 0.731 seconds. So the time for one complete rotation is 0.731 seconds. So velocity is 2 pi r divided by the period, and that gives us 10.30 meters per second. We're going to substitute that in to find the acceleration. So acceleration is 10.30 meters per second squared divided by 1.2, and that gives us a centripetal acceleration of 88.48 meters per second squared. Now I can solve for mass. 170 newtons divided by 88.48 meters per second squared gives me a mass of 1.92 kilograms. Corrected to two significant figures is 1.9 kilograms. And you're good to work on the DN9 assignment.